November 14th, 1877. Marion, Ohio. The limestone ledge that would change American engineering forever was about to claim its first victim. Henry Marion's revolutionary wire rope steam shovel, the machine that European engineers swore would fail catastrophically, had been running for over 300 consecutive hours without a single breakdown. Traditional chain-driven shovels from Boston's finest manufacturers collapsed every 6 weeks. Marion's system just kept digging. Through the steam and grinding steel of the Great Lakes Canal construction site, something impossible was happening. American wire rope technology was outperforming European chain systems that had dominated excavation for decades. 114 individual steel wires working together where European engineers insisted only solid chain links could handle the stress. Wilhelm Hoffman's engineering reports declared it mechanically unsound. Sir Charles Pemberton's Cambridge education told him it would kill workers. Yet Marion's shovels moved over 1,200 tons per day, while European machines struggled with 340. Then the 4-ton limestone load hit Marion's flagship shovel. In the next 30 seconds, everything European engineers predicted about American innovation would either be proven right or proven catastrophically wrong. Spring air carried coal dust and machine oil across the muddy construction site where Henry Marion stood studying the wreckage of another European steam shovel. The massive chain-driven excavator had lasted exactly 41 days before its main hoist chain snapped under a 2-ton load, sending the bucket crashing into the canal bed with enough force to crack the limestone beneath. It was the third catastrophic failure in as many months on the Great Lakes Canal project, and Marion could see the fear creeping into his workers' eyes every time they approached the remaining European machines. The canal itself represented America's boldest engineering gamble, a 23-mile waterway that would connect Lake Erie directly to Ohio's richest coal fields, bypassing the expensive railroad monopolies that strangled industrial growth. 847 tons of coal needed to move through this channel daily to fuel the expanding railroad network that was stitching the continent together. But the European steam shovels that dominated American construction could barely manage 340 tons before breaking down completely, their rigid chain systems failing catastrophically under the constant stress of moving Ohio's stubborn clay and limestone. Marion walked the perimeter of the broken machine, his railroad foreman instincts cataloging every failure point. The chain hoist system that Boston engineering firms Wilhelm Hoffman called the pinnacle of excavation engineering consisted of solid iron links connected in sequence, each link carrying the full load of whatever the shovel attempted to lift. When one link failed, as they inevitably did under repeated stress, the entire system collapsed instantly. Marion had watched 3 men die in a similar chain failure during his Pennsylvania Railroad days, crushed when a locomotive hoist gave way without warning. The memory drove him to question every piece of equipment that depended on single point of failure designs. Tim O'Sullivan approached from the remaining functional shovel, his Irish accent thick with frustration. "Another day, another breakdown, Henry. The boys are saying maybe the Europeans know something we don't." O'Sullivan had operated steam shovels longer than anyone on the project, his hands reading vibrations and stress patterns through the controls like a musician feeling rhythm. If he was losing confidence in American methods, the entire crew would follow. Marion pulled a folded letter from his coat pocket, correspondence from John Roebling's wire rope factory in Trenton, New Jersey. Roebling had revolutionized suspension bridge construction by replacing hemp ropes with twisted steel cables, and his latest innovation promised to transform excavation machinery. Instead of solid chains that failed completely when any single link broke, Roebling's wire rope distributed loads across 114 individual steel wires woven into 6 strands of 19 wires each. If 10 wires snapped, the remaining 104 continued carrying the load. "What if chains aren't the answer?" Marion asked O'Sullivan, showing him Roebling's technical drawings. "Look at this construction. 6 strands, 19 wires per strand, each wire taking part of the load. No single point of failure." O'Sullivan studied the diagrams with the skepticism of a man who had seen too many engineering promises turn into worker funerals. Looks complicated, Henry. More parts means more things to break. Or more ways to stay working when something does break, Marion countered. He had been running calculations for weeks, comparing the failure patterns of chain systems against the distributed load principles that made Roebling's bridge cables legendary for reliability. European engineers built systems that worked perfectly until they failed completely. American innovation might build systems that degraded gradually, giving operators warning and time to react. The next morning brought Wilhelm Hoffmann's inspection tour, the Prussian-trained engineer arriving with his customary retinue of assistants and measuring instruments. Hoffmann commanded respect through his encyclopedic knowledge of classical engineering principles and his ability to calculate load stresses using formulas developed in German technical academies. When he examined the broken chain hoist, his diagnosis was swift and authoritative. Predictable failure under cyclical loading, Hoffmann announced to the gathered supervisors. The metallurgy is sound, but no chain system can withstand infinite stress cycles. We must accept that excavation machinery requires regular replacement of wear components. His solution involved ordering identical replacement chains from Boston engineering firm, accepting the 6-week failure cycle as an unavoidable cost of construction. Marion stepped forward with Roebling's wire rope specifications. What about distributed load systems? Instead of chains that fail completely, cables that degrade gradually? Hoffmann's expression shifted to the patient condescension he reserved for American contractors who ventured beyond their expertise. Wire rope systems are mechanically unsound for excavation work. The flexibility that makes them suitable for static bridge applications becomes dangerous under dynamic loading. When, not if, these overcomplicated cables fail, they will kill workers and bankrupt this project. The confrontation escalated when Sir Charles Pemberton arrived for his weekly progress review. The Cambridge-educated project supervisor possessed the institutional authority to approve or reject any technical modifications, and his British engineering background aligned him naturally with European methods. Marion presented his wire rope proposal with detailed cost analyses and performance projections, but Pemberton's response was immediate and final. The double drum chain hoist system, pioneered by established manufacturers, represents proven technology, Pemberton declared. I cannot authorize experimental methods when worker safety and project completion depend on reliable equipment. His report to the canal's financial backers would describe Marion's wire rope idea as dangerous improvisation by contractors unfamiliar with proper engineering principles. Within 48 hours, Marion's financial supporters began withdrawing their commitments. The combination of European engineering authority and repeated chain system failures created a perfect storm of lost confidence. Investors who had initially supported American innovation now feared association with methods that established experts publicly condemned as unsafe. By month's end, Marion faced $23,000 in debt, 200 unemployed workers, and a half-built canal that European engineers called impossible to complete with American methods. The wire rope revolution would either prove itself through performance or destroy everything Marion had built trying. The train whistle that announced Marion's arrival at John Roebling's Trenton factory carried the weight of desperation. With his financial backers gone and his reputation in ruins, Marion had converted every remaining asset into a single catastrophic gamble, the largest wire rope order in American industrial history. 47,000 feet of steel cable would either vindicate his engineering vision or complete his professional destruction. Roebling's factory operated with methodical German precision, each manufacturing station coordinated to produce wire rope that met specifications measured in fractions of inches. The new 80-ton wire rope machine dominated the main production floor, its massive spools capable of producing 30,000 feet of continuous cable without the weak splices that had plagued earlier attempts at long-span construction. Marion watched 6 separate wire-drawing operations feed raw steel into the twisting mechanism that would create his revolution. Your specifications call for 1.5-inch diameter cable with 6 strands of 19 wires each, Roebling said, consulting the engineering drawings spread across his office table. The 6/19 construction creates perfect hexagonal strand patterns, but I must warn you about the cost implications. This represents more steel cable than my factory typically produces in 3 months. Marion had calculated those costs down to the final dollar. The wire rope would cost 3 times more than equivalent chain systems, but if his performance projections proved accurate, the investment would pay for itself within 6 months through reduced downtime and increased excavation capacity. Can your machine produce the full order as continuous lengths? No splices? No weak points? Continuous production up to 10,000 feet per cable run, Roebling confirmed. But I need your guarantee that these cables will be properly terminated. Wire rope strength depends entirely on end fittings that distribute loads across the full cable's circumference. Improper termination can reduce rope strength by 30% or more. The technical specifications that Roebling outlined represented years of engineering evolution. Each wire strand consisted of 19 individual steel wires, twisted in a precise helical pattern, with 3 different wire gauges combined to create maximum strength and flexibility. The 6 strands were then twisted around a steel core in the opposite direction, creating a rope structure that became stronger under load rather than weaker. Unlike chain systems where failure of any single link destroyed the entire mechanism, wire rope distributed stress across 114 individual load-bearing elements. Marion spent 3 days at the Trenton factory, learning every aspect of wire rope construction and installation. Roebling's engineers demonstrated proper cable termination techniques using mechanical sockets that gripped the full rope circumference, distributing terminal loads across every individual wire. The process required precision that chain installation never demanded, but the result was a connection that maintained 100% of the cable's rated strength. The first shipment arrived at the Marion construction site on a muggy July morning, 23,000 feet of steel cable coiled on massive wooden spools. Tim O'Sullivan and the remaining crew gathered around the shipment with the mixture of curiosity and skepticism that greeted every departure from established methods. The wire rope looked impossibly flexible compared to the rigid chain systems they knew, its surface smooth and continuous where chains showed obvious weak points at every link junction. "Looks like ship's rigging more than excavation equipment," O'Sullivan observed, running his hands along the cable's surface. "How's this supposed to handle 2-ton bucket loads when it bends like hemp rope?" Marion had prepared for exactly that question. He rigged a test apparatus using the factory's strongest overhead beam, suspending a 3-ton load from a single wire rope sample. The cable stretched slightly under load, but showed no signs of distress. It's a distributed structure absorbing stress that would have snapped a chain link instantly. When he added an additional half-ton load, the wire rope continued holding steady while showing measurable but manageable elongation. The conversion of Marion's first steam shovel took 18 days of precise mechanical work. Every chain component required replacement with wire rope equivalents, from the main hoist cables to the auxiliary draglines that positioned the shovel during operation. The drum systems needed modification to accommodate wire rope's different winding characteristics, and the operators required training to recognize the subtle performance differences between cable and chain systems. James McCarthy supervised the installation with his characteristic attention to detail, checking every terminal connection against Roebling's specifications and testing each system component under gradually increasing loads. As construction supervisor, McCarthy understood that any failure would endanger not just the project timeline, but the lives of workers who depended on equipment reliability. His methodical approach to safety protocols had kept the crew accident-free through 3 chain system failures. The prototype shovel's first operational test began at dawn on August 15th. Marion positioned himself at the controls while O'Sullivan and McCarthy monitored the wire rope systems for any signs of stress or malfunction. The initial bucket load, 1.5 tons of Ohio limestone, lifted smoothly with none of the jerking motion that characterized chain-driven systems. The wire rope's inherent flexibility absorbed shock loads that would have stressed metal chains to their breaking point. By noon, the performance differences had become undeniable. Marion's wire rope shovel lifted 2 3/10 tons per bucket, 40% more capacity than the European chain systems. The distributed load structure eliminated the sudden stress spikes that caused chain failures, allowing operators to work at maximum capacity without fear of catastrophic breakdown. More importantly, the wire rope system showed no signs of fatigue after 6 hours of continuous operation. Word spread through Ohio's industrial community with the speed that accompanied any genuine breakthrough. Railroad contractors, canal builders, and mining engineers began arriving at the Marion site to witness wire rope technology firsthand. The visitors brought skepticism rooted in decades of chain system experience, but Marion's shovel continued operating day after day without the breakdowns that punctuated traditional excavation work. By September, the prototype had achieved 73 consecutive operating days without system failure, a performance record that no chain-driven shovel had ever approached. The wire rope's distributed load principle was proving itself through the only test that mattered to American contractors: practical results under working conditions. Marion's gamble on continuous cable production and proper termination techniques had created excavation capabilities that European engineering theory claimed were impossible. The arrival of Hoffman Engineering's Model 1876 steam shovel transformed the Great Lakes Canal project into America's most watched industrial competition. The massive European machine dominated the construction site like a mechanical cathedral, its 3.5 cubic yard bucket dwarfing Marion's wire rope prototype by nearly 50%. Wilhelm Hoffman had designed this machine specifically to demonstrate American methods' inferiority, incorporating every refinement that Prussian engineering could devise. Hoffman's shovel represented the pinnacle of chain-driven technology, its double-drum hoist system featuring hardened steel links manufactured to tolerances measured in thousandths of inches. The main boom stretched 68 feet from pivot to bucket, creating leverage ratios that European calculations showed would generate maximum digging force. Every component reflected decades of German Technical Academy refinement, from the steam engine's compound cylinders to the gear reduction systems that multiplied operator control into massive mechanical advantage. "This machine will settle the question permanently," Hoffman announced to the crowd of engineers and contractors who had gathered for the public demonstration. European chain systems represent mature technology perfected through generations of practical application. American wire rope experiments cannot compete with proven engineering principles. Sir Charles Pemberton had approved the demonstration as a definitive test of excavation methods, positioning both machines side by side in the canal's deepest section, where 83 feet of limestone and clay awaited removal. The geological conditions represented the worst possible challenge: compressed limestone that required maximum force to break, underlaid with clay that created unpredictable load conditions as buckets pulled free from the excavation face. Marion positioned his wire rope shovel adjacent to Hoffman's machine, the size difference creating visual drama that favored European technology. Spectators lined the canal banks while newspaper reporters documented every detail of what industry publications were calling the Sioux Great Excavation Trial. The stakes extended beyond simple performance comparison. Whichever system proved superior would likely dominate American construction for decades. The competition began at sunrise, with both machines attacking the limestone face simultaneously. Hoffman's European shovel initially demonstrated clear advantages, its massive bucket biting deeper into the rock while generating digging forces that Marion's smaller machine could not match. The chain-driven system's rigid connections transmitted power efficiently from steam engine to cutting edge, creating the mechanical precision that German engineering principles demanded. Tim O'Sullivan operated Marion's wire rope shovel with the careful attention to stress patterns that 15 years of excavation experience had taught him. The distributed load system allowed him to sense bucket conditions through subtle changes in cable tension, adjusting his approach to minimize shock loads that might stress individual wire strands. European operators worked with binary feedback, chains either held or broke, but wire rope provided continuous information about system stress levels. By the third day, both machines had established working rhythms that revealed their fundamental design philosophies. Hoffman's chain system attacked the excavation face with mechanical precision, each bucket load calculated to maximize the rigid system's advantages. Marion's wire rope shovel worked with fluid adaptability, its flexible cable system absorbing shock loads and adjusting to varying geological conditions automatically. The first significant stress test came when both machines encountered a limestone ledge that had resisted earlier excavation attempts. Hoffman's European shovel applied maximum force through its chain system, the rigid links transmitting engine power directly to the bucket without any load absorption. The limestone resisted initially, then broke away suddenly in a massive chunk weighing approximately 4 tons, well within the machine's rated capacity but representing an instant shock load that stressed every system component. Marion's wire rope system handled similar limestone challenges through distributed loading that spread shock forces across 114 individual wire strands. When his bucket broke free limestone chunks of comparable size, the wire rope stretched slightly to absorb the impact energy before returning to normal operating tension. O'Sullivan could feel the difference through the controls. Wire rope systems provided warning of excessive loads while chains simply held until catastrophic failure. The performance gap became measurable as working days accumulated. Hoffman's European machine initially moved more material per hour due to its larger bucket capacity, but increasing chain wear began reducing operational efficiency. Stretched chain links created alignment problems that required constant adjustment, while worn pivot points introduced mechanical sloppiness that affected digging precision. By the 6th week, the European machine required daily maintenance that reduced actual working time to fewer than 8 hours per day. Marion's wire rope shovel maintained consistent performance throughout the competition period. Individual wire breaks occurred occasionally, visible as slight fraying at stress points, but the distributed load system continued operating without performance degradation. Weekly cable inspections revealed predictable wear patterns that allowed scheduled maintenance rather than emergency repairs. The machine typically operated 10 hours daily with routine lubrication and tension adjustments that required minimal downtime. The catastrophic moment arrived during the competition's 8th week, when both machines were attacking the most challenging section of limestone face. Hoffman's European shovel had been showing increasing signs of chain system stress, elongated links, binding pivot points, and irregular load transmission that created vibrations throughout the machine frame. O'Sullivan had warned Marion about similar warning signs during his Pennsylvania Railroad days, but European operators lacked experience recognizing distributed system failure patterns. The failure occurred at hour 180 of continuous operation. Hoffman's main hoist chain, stressed by weeks of maximum loading cycles, reached its fatigue limit while lifting a 2 1/10 ton load of broken limestone. The failure began at a single link that had developed microscopic cracks invisible to visual inspection, but once that link snapped, the entire chain system collapsed instantly. The loaded bucket crashed into the canal bed with enough force to crack the underlying bedrock, while the sudden load release damaged steam engine components and bent the main boom structure. Marion's wire rope shovel continued operating through the European machine's destruction, its distributed load system showing no signs of equivalent stress. The psychological impact on spectators was immediate and dramatic. European chain technology had failed catastrophically, while American wire rope methods continued working without interruption. The demonstration had provided exactly the definitive comparison that industrial observers demanded, but the results directly contradicted expert predictions. By autumn's end, Marion operated his wire rope shovel for 318 consecutive hours, moving 1,247 tons of material while Hoffman's European machine sat disabled, awaiting replacement parts that would require months to manufacture and ship from German factories. The limestone ledge that would destroy Marion's reputation had been resisting excavation for 3 weeks, its crystalline structure harder than any material the wire rope shovels had previously encountered. James McCarthy studied the geological formation with growing concern, recognizing stress patterns that had claimed equipment and lives during his 15 years of construction supervision. The ledge extended 47 feet horizontally and rose nearly 12 feet above the canal floor, creating an excavation challenge that would test every limit of wire rope technology. Marion's flagship shovel had been operating flawlessly for 8 months, its performance record silencing European critics who had predicted catastrophic wire rope failures. The machine's daily output exceeded 1,200 tons, triple the capacity that Wilhelm Hofmann's chain systems had achieved before their breakdown. Industrial observers from across America made regular pilgrimages to witness wire rope technology firsthand, and Marion's order books filled with contracts that represented the future of American excavation. The final phase of canal construction required removing this massive limestone obstacle, but geological surveys revealed internal fractures that made conventional excavation extremely hazardous. McCarthy coordinated the attack using controlled blasting to crack the formation before mechanical removal, but the resulting limestone chunks weighed far more than normal bucket loads. Some pieces approached 4 tons, still within the wire rope system's rated capacity, but representing stress levels that no American excavation equipment had previously sustained under working conditions. Tim O'Sullivan operated the flagship shovel with heightened attention to cable behavior, his experienced hands reading tension variations that indicated how the distributed load system was responding to unprecedented challenges. Wire rope technology provided continuous feedback about stress distribution, unlike chain systems that offered no warning before catastrophic failure. O'Sullivan could feel individual wire strand conditions through subtle control responses, adjusting his technique to minimize shock loads on the most stressed cable sections. The morning of November 14th began with unusual atmospheric conditions that experienced operators recognized as potentially dangerous. High humidity combined with temperature variations created condensation that made cable surfaces slippery, while barometric pressure changes affected steam engine performance in ways that altered power delivery characteristics. McCarthy postponed the day's most challenging lifts until conditions improved, but the limestone ledge continued blocking canal completion with each passing day, costing the project hundreds of dollars. Marion made the decision to proceed with excavation despite environmental concerns, calculating that wire rope's distributed load advantages would overcome the marginal increase in operating risks. The flagship shovel had demonstrated remarkable reliability under extreme conditions, and the limestone removal represented the final obstacle to canal completion. Financial pressure from investors demanded progress, while construction crews waited for resolution, before beginning final grading operations. The critical lift began at 10:47 in the morning, O'Sullivan positioning the bucket to engage a limestone chunk, the geological assessment estimated at approximately 4 tons. The wire rope system initially handled the load normally, 114 individual wire strands sharing the stress as Roebling's engineering principles intended. Cable tension gauges showed readings within normal parameters, while steam pressure remained steady as the bucket began its upward movement. The failure occurred without warning at maximum lift height, when sudden geological shifting caused the limestone chunk to twist during extraction. The rotational force created lateral stress patterns that the wire rope's terminal connections were never designed to handle, concentrating loads on cable end fittings rather than distributing them across the full rope circumference. In the space of 3 seconds, terminal stress exceeded the rope's rated capacity by nearly 30%. All 114 wires failed simultaneously as the inadequate end fittings pulled apart under the combined vertical and lateral loads. The 4 2/10 ton limestone chunk plummeted 37 feet into the canal bed, creating an impact crater that measured 8 feet across and penetrated 18 inches into the bedrock below. The massive bucket followed, its weight adding to the destruction as twisted steel and shattered stone created chaos that would haunt American wire rope development for years. James McCarthy was standing directly beneath the lift trajectory, coordinating ground crews who were preparing to guide the extracted limestone away from the working area. The falling debris struck him with enough force to cause instantaneous death, his body crushed beneath limestone chunks that no human reflexes could have avoided. The tragedy transformed what should have been a routine excavation operation into the worst accident in canal construction history. Wilhelm Hofmann arrived at the disaster site within hours, his engineering team documenting every detail of the wire rope failure for the comprehensive report that would vindicate European chain technology. His preliminary assessment focused on the catastrophic nature of distributed system failure, arguing that when wire rope systems collapsed, they created more dangerous conditions than equivalent chain breakdowns. European chain failures typically occurred gradually, providing operators with warning time that wire rope's sudden failure mode eliminated. American wire rope systems fail more catastrophically than chains, Hoffman declared in his official report. This technology is fundamentally flawed because it concentrates terminal stresses beyond safe engineering margins. When distributed load systems reach their failure point, they collapse without warning in ways that endanger every worker in the immediate area. His analysis concluded that wire rope technology represented dangerous experimentation that sacrificed proven safety for theoretical performance advantages. The aftermath brought complete work stoppage as state investigators examined every aspect of the accident. Marion faced criminal charges for criminal negligence, with prosecutors arguing that his experimental wire rope technology created unnecessary risks for workers who depended on equipment reliability. The canal's financial backers withdrew support immediately, unwilling to associate with methods that had claimed a supervisor's life in such a public and dramatic fashion. The detailed engineering investigation that followed revealed the true cause of the catastrophe. Wire rope failure had occurred not because of inherent technology flaws, but because improper terminal connections had reduced the cable's effective strength by exactly 30%. The mechanical sockets that Roebling had specified for proper load distribution had been modified during installation to reduce costs, creating weak points that concentrated stress on inadequate end fittings rather than distributing loads across the full cable circumference as designed. The letter from Charles G. Roebling arrived at Marion's temporary office 3 weeks after James McCarthy's funeral, carrying engineering solutions that would either redeem wire rope technology or confirm its fundamental inadequacy. The younger Roebling had spent months analyzing the canal disaster, applying metallurgical principles his father had developed for suspension bridge construction to the specific challenges of excavation equipment. His proposed modifications addressed the terminal connection failures that had killed McCarthy and destroyed Marion's reputation. Marion studied Roebling's technical drawings with the desperate intensity of a man facing professional extinction. The improved closing techniques eliminated the cost-cutting modifications that had reduced cable strength by 30%, replacing them with mechanical sockets that gripped the full rope circumference and distributed terminal loads across every individual wire strand. The new system required precision machining that would double terminal connection costs, but Roebling's calculations showed the result would maintain 100% of the cable's rated strength under any loading condition. Criminal charges still hung over Marion's head, while European engineers proclaimed wire rope technology permanently discredited. Wilhelm Hoffman's comprehensive report had convinced most American contractors that distributed load systems represented dangerous experimentation that sacrificed worker safety for theoretical performance gains. The canal project remained suspended indefinitely, with investors unwilling to fund any continuation of wire rope excavation methods. Tim O'Sullivan remained loyal despite offers from established contractors who used proven chain technology. His hands still carried the memory of detecting stress patterns through wire rope controls, and his engineering instincts told him the system's fundamental principles were sound despite the tragic terminal connection failure. "The cable itself never broke, Henry," he reminded Marion during their planning sessions. "Every wire held until the end fittings pulled apart. Fix the terminals, and you fix the problem." The technical solution required complete redesign of every cable termination point on Marion's remaining shovels. Roebling's mechanical sockets used compression fittings that surrounded the cable end with hardened steel sleeves, distributing terminal loads through friction contact across the entire rope circumference rather than relying on individual wire grip strength. The installation process demanded precision that chain systems never required, but the result was a connection that became stronger under load rather than weaker. Marion invested his remaining resources in the terminal connection upgrades, working with a skeleton crew of volunteers who believed wire rope technology could overcome its initial setback. The improved sockets required custom machining at Roebling's Trenton facility, where each fitting was manufactured to tolerances measured in thousandths of inches and tested under loads exceeding operational requirements by 50%. The modified wire rope system underwent extensive testing before returning to canal construction. Marion personally supervised every lift, gradually increasing bucket loads while monitoring cable behavior for any signs of stress concentration or terminal slippage. The improved sockets performed flawlessly, maintaining full cable strength under dynamic loading conditions that had previously caused catastrophic failure. More importantly, the distributed load principles continued providing the operational advantages that had made wire rope superior to chain systems. Public rehabilitation began slowly as the upgraded shovels demonstrated consistent reliability throughout the winter months. Marion's machines excavated the remaining canal sections without system failures, their performance gradually rebuilding confidence among contractors who had witnessed the earlier disaster. The wire rope shovels completed challenging geological formations that had defeated European chain systems, proving that proper terminal connections eliminated the safety concerns that critics had raised. The breakthrough came during the canal's final construction phase, when Marion's improved wire rope system achieved performance records that vindicated American engineering innovation. The upgraded shovels operated from December 1877 through completion in July 1879, 583 consecutive working days with routine maintenance but zero system failures. This operational reliability exceeded anything that chain-driven systems had ever accomplished, establishing wire rope technology as demonstrably superior to European methods. Industrial observers who had dismissed wire rope technology after the terminal connection disaster returned to witness the completed canal's opening ceremonies. The waterway moved 1,200 tons of coal daily, triple the original design requirements, and 4 times the capacity that European chain systems had achieved before their breakdown. Marion's excavation methods had not only solved the technical challenges, but created capabilities that transformed regional industrial development. The completed Great Lakes Canal became a showcase for American engineering innovation, its success leading to wire rope adoption throughout the construction industry. Within 2 years, virtually all major American excavation manufacturers were converting their steam shovel designs from chain to cable systems, while European companies struggled to compete with outdated technology that could no longer match American performance standards. Marion's vindication extended beyond simple technical success to establish new principles for American industrial development. The wire rope revolution demonstrated that distributed systems could outlast single point of failure designs when properly engineered, creating reliability through complexity rather than simplicity. European engineering traditions that emphasized proven methods and conservative innovation were giving way to American approaches that embrace systematic experimentation and performance-based validation. The Marion Steam Shovel Company, founded in 1884, became one of America's dominant excavation manufacturers by building exclusively wire rope machines. Marion's shovels later helped dig the Panama Canal, where 77 Marion machines outperformed European competitors using chain technology that had become obsolete. The company's success represented more than individual triumph. It marked America's emergence as the world's leading source of industrial innovation. The broader impact of Marion's wire rope revolution extended throughout American engineering, establishing distributed load principles that would influence everything from elevator systems to mining equipment. His success proved that American ingenuity could overcome established European expertise through systematic improvement rather than revolutionary breakthrough. The canal that had nearly destroyed his career became the foundation for engineering approaches that would define American industrial leadership for generations. The limestone ledge that had killed James McCarthy was finally removed using Marion's improved wire rope system, its extraction completed without incident through proper terminal connections that distributed loads as Roebling's original design intended. The tragedy that had threatened to end wire rope development ultimately led to engineering refinements that made distributed systems safer and more reliable than the chain technology they replaced.